Welcome back. Today we're tackling the challenges in LLM development, the obstacles researchers and engineers face when building these powerful systems.
Despite all the progress, LLMs have significant limitations and problems that the field is actively working to address.
Let's start with one of the most talked about issues hallucination. What exactly is it?
Hallucination is when a model generates information that sounds plausible but is actually false or unsupported by its training data or provided context.
The model might confidently state incorrect facts, invent citations that don't exist, or fabricate details about events that never happened.
This happens because LLMs are trained to predict plausible sounding text, not to verify truth. The objective is livelihood, not accuracy.
Hallucination is particularly dangerous in high stakes applications like medical advice, legal reasoning, or factual reporting.
Mitigation strategies include retrieval augmented generation, which grounds responses in verified sources, and training models to express uncertainty when they don't know something.
But completely eliminating hallucination remains an open challenge.
Another major issue is bias. LLMs reflect and can amplify biases present in their training data.
This includes gender bias, racial bias, cultural bias, and biases around age, disability, religion, and other attributes.
For example, a model might associate certain professions more with one gender or produce different quality outputs depending on the perceived demographics of the person described in the prompt.
Bias is particularly insidious because the training data scraped from the internet reflects historical and societal biases.
Addressing bias requires careful data curation, debiasing techniques during training, and extensive testing and red teaming.
But it's challenging because bias can be subtle, context dependent, and there's debate about what constitutes fair or unbiased behavior.
Let's talk about interpretability. Despite their capabilities, LLMs are largely black boxes.
We don't fully understand how they arrive at their outputs. Why did the model generate this particular response? What internal representations led to this decision?
This lack of interpretability makes it hard to debug failures, verify safety, or build trust in high stakes applications.
Researchers use techniques like attention visualization, feature analysis, and activation patching to peer inside models.
But these provide only partial views. The full computation involves billions of parameters and complex interactions that are difficult to interpret.
Another challenge is compute cost. Training frontier LLMs requires enormous computational resources.
We're talking millions of dollars in GPU or TPU time, weeks or months of training, and significant energy consumption.
This creates barriers to entry. Only well funded organizations can train the largest models.
It also raises sustainability concerns. The carbon footprint of training large models is substantial.
There's active research into more efficient training methods, better architectures, and hardware improvements.
But for now, compute cost remains a major constraint on who can develop frontier AI.
Even inference, running the model after it's trained, can be expensive for very large models.
Serving billions of queries requires significant infrastructure. This is why techniques like quantization, distillation, and efficient attention are so important.
Let's discuss data quality and availability. LLMs need vast amounts of text data.
But high quality data is finite. We're approaching limits on how much text is available on the internet.
This has led to interest in synthetic data, using models to generate training data for other models.
But there are concerns about model collapse. If models are increasingly trained on synthetic data from other models, quality might degrade over generations.
Data privacy is another issue. Training data might include personal information, copyrighted material, or sensitive content.
There are legal and ethical questions about using such data and technical challenges in scrubbing it effectively.
Let's talk about catastrophic forgetting, which we mentioned earlier.
When you fine tune a model on a narrow task, it can lose capabilities it had after pre training.
The parameters get overwritten with task specific knowledge, degrading performance on other tasks.
This makes it challenging to continually update or adapt models without degrading them.
Techniques like regularization toward the original weights, mixing in general data during fine tuning, or using parameter efficient methods can help.
Another challenge is robustness. LLMs can be brittle to input variations.
Small changes to the prompt, rephrasing the question, changing capitalization, adding irrelevant context can sometimes dramatically change the output.
This inconsistency makes models less reliable. Ideally, semantically equivalent inputs should produce equivalent outputs.
Adversarial robustness is also a concern. Bad actors can craft inputs designed to make the model misbehave.
Prompt injection attacks try to override the model's instructions by embedding malicious instructions in user inputs.
Jailbreaks attempt to bypass safety guardrails and elicit harmful or prohibited outputs.
Red teaming helps find these vulnerabilities, but it's a cat and mouse game. New attack methods keep emerging.
Let's discuss mode collapse in generation. Sometimes models produce repetitive or overly generic outputs,
The model might get stuck in loops, repeating the same phrase over and over.
or it might produce safe but uninteresting responses that lack diversity.
This can happen due to exposure bias, the mismatch between training where the model sees correct previous tokens and generation where it sees its own predictions.
Techniques like sampling with temperature, nucleus sampling, and repetition penalties help increase diversity.
Another challenge is context length. Transformers have limited context windows, typically a few thousand to tens of thousands of tokens.
This limits the amount of information the model can consider at once. You can't feed it a whole book or long conversation history.
Attention's quadratic complexity makes very long context expensive. Recent models have extended context to 100K or even 1 million tokens, but this requires architectural innovations.
There's also the issue of long range coherence. Even when models can handle long contexts, maintaining consistency and coherence over long outputs is challenging.
The model might contradict itself, forget earlier details, or drift off topic.
Let's talk about preference drift. When you fine tune with RLHF or other preference methods, the model's behavior changes.
Sometimes this optimization leads to unintended consequences. The model might become overly verbose, excessively cautious, or sycophantic.
It learns to game the reward model rather than genuinely improving on the intended dimension.
This is called reward hacking or Goodhart's law. When a measure becomes a target, it ceases to be a good measure.
Careful reward model design and regularization help, but it remains a challenge.
Another issue is calibration. LLMs often express confidence that doesn't match their actual accuracy.
They might state false information with high confidence or be uncertain about things they actually know.
This makes it hard for users to know when to trust the model.
Better calibration requires specialized training or post processing, but it's an active research area.
Let's discuss multilinguality. Most LLMs are primarily trained on English text.
They perform worse in other languages, especially low resource languages with limited training data.
Building truly multilingual models that perform equitably across languages is challenging.
It requires balanced multilingual training data, appropriate tokenization, and sometimes language specific adaptations.
Finally, there's the challenge of alignment, ensuring models behave in ways that align with human values and intentions.
This goes beyond just avoiding harmful outputs. It includes being helpful, truthful, nuanced, and appropriately cautious.
Alignment is fundamentally difficult because human values are complex, context dependent, and sometimes contradictory.
Different users and cultures might have different preferences, and it's not clear how models should navigate these differences.
So, to recap, LLMs face challenges with hallucination, bias, interpretability, compute cost, data quality, catastrophic forgetting, robustness to adversarial attacks, mode collapse, context length limitations, preference drift, calibration, multilinguality, and alignment.
These aren't just technical problems, they involve ethical, social, and philosophical questions about how AI should behave.
Next episode, we're diving into transfer architectures in depth, starting with what transfer architecture actually means.
Thanks for listening.
Until next time, keep learning and stay curious about AI.